So all of you, okay, I think there is no offline classes for you as of now, for the final years. Okay, we're going online mode itself. And we have completed regarding BTD, we have completed the work and heat, uh, which gives the basics of the parameters, how to calculate the work. But I think you have not learned how to calculate the heat from 1 to 2. So you have learned how to calculate the work from 1 to 2. That is for all the 5 processes. And how to calculate the heat from 1 to 2 for all the 5 processes, you haven't learned it. Yes or no? Did I teach you how to calculate the heat flows for the process 1 and 2? Yes. Yes or no, man? Varun, Varun Pujari. Am I audible, by the way, first of all?
Yes, sir.
Okay. So then why no one are responding now? Anish Pinto, Chiran.
I was not there before, so I don't know whether he
Okay,
had.
okay. Chiran.
Sir, I was absent yesterday.
Okay. Devdash. Devdash. Ashir.
Yes, sir.
Okay, is my voice breaking?
Sir, I joined now only, sir.
Okay. Fine. Uh, others can answer it. Is my voice breaking for everyone?
No,
No,
sir.
sir, no.
Okay. Only for Nishan Shetty and few. Numan Ahmad also. The internet is fine. It's fully connected. Okay, so in this class, we'll start the first law of thermodynamics. So the laws of thermodynamics are two basic laws are there. The first one is the first law, second one is the second law of thermodynamics. These two are so important that I will be using all the way throughout. So understanding the concepts of work and heat, understanding the first law, and understanding the second law will complete your understanding in the thermodynamics. So whatever you require from the thermodynamics, that is only with respect to these three chapters. Number one is the work and heat. Number two is the first law. Number three is the second law of thermodynamics. So understand this very, very well. So these are very important for the examinations. And today, whatever we will be covering are so important. So we'll be covering the Joules experiment, first law statements for both cyclic and non-cyclic processes, energy as a property of a system, and the heat expressions for all the 5 processes. So all this content will be covering today. So it's a very important class. I want you to be concentrative and reactive too. Okay. So how many of you know the law of conservation of energy? So this law is most popular law. Everyone will be at its tongue tips for this particular law. So this is easy to understand, easy to remember, everything. So how many of you know the law of conservation of energy?
Energy can neither be created nor destroyed.
Yes, but it can be transferred from one form to the other.
One
So
form.
yes, exactly. The whole universe follow this particular law. There is no substitution for this law. It says you cannot create energy or you cannot destroy an energy, but what you can do, you can just transfer from one form to the other form. So that is the only thing you can do with concern with the energy. So that is a beautiful statement, which is known as law of conservation of energy. And your first law of thermodynamics draws its principles from this law of conservation of energy. In order to understand the first law, let us look into the Joules experiment, which is this. So in this particular Joules experiment, what he has done is he has taken a water bath like this, okay, and he has incorporated a thermometer, and he has put a pedal wheel. Okay, so initially what he has done is he has just rotated this pedal wheel or agitator. Okay, as and when he has rotated this uh, agitator, is the whole mixture, whether the temperature increases or decreases. Okay, let me ask you in this way. So you're transferring work into the system. That means you're working on the system. You're transferring work to the system. So what happens to your temperature is temperature naturally increases like this. Because why? Because you're transferring work into the system. Okay. So he has noted down what amount of work he has transferred into the system. Say it is 10 watt or 10 kilowatt of work he has transferred into the system. Okay, once he has transferred, he has totally taken out the thermometer, he has kept the thermometer and taken out the pedal wheel. And what he has done is he has totally incorporated this in a water bath. So what he has done, he has just kept this the whole thing in a water bath like this. Okay. So once he has kept in a water bath like this, what happens? The temperature, which is at the higher level inside, will naturally flow to the water bath. Yes or no? Correct? Once it has flown, he has noted down the value of Q, guys. And shockingly, he found that what he has noted down the value of W, it was 10 kilowatts, is it? 10 kilowatts. That is the work transfer initially which he has done. Secondly, when he introduced a water bath and calculated the amount of Kev that is transferred to the water, even that was also 10 kilowatt. Surprisingly, he found that whatever work he has transferred and whatever heat he has gained back, both the things are same. Thereby, he gives the first law of thermodynamics as the cyclic integral of work flows will be equal to cyclic integral of heat flows. This is your first law. Keep it simple, man. Don't make it too much complicated. Okay, I will never teach you in a textbook language, in a low level language. Understand the concepts. That's very important. So, what is the first law state? First law says the cyclic integral of work flows will be equal to the cyclic integral of heat flows. Everyone got this? What is the first law of thermodynamics? Yes, Hashir?
Yes.
Cyclic integral of work
Uh-huh.
is equal to cyclic integral of heat.
Heat flows. That's it. Abdul Rahim. Abdul Rahim. Abdul Rahim.
Yes, sir.
So,
Yes, sir.
yes. So, what do you mean
Cyclic
by
integral of work is equal to cyclic integral of heat.
heat flows? Narendra, ಅರ್ಥ ಆಗಿಲ್ವೇನೋ? Narendra, it's very simple. Look here. So,
ಇಲ್ಲ ಅರ್ಥ
initial,
ಆಗಿಲ್ಲ.
ಅರ್ಥ ಆಯ್ತಾ?
ಇಲ್ಲ ಆಗಿಲ್ಲ ಸರ್.
ಓಕೆ, ಇಲ್ಲಿ ಕೇಳಿ. ಏನ್ ಮಾಡಿದ್ದಾನೆ ಅಂತಂದ್ರೆ, ಒಂದು ವಾಟರ್ ಬಾತ್ ತಕೊಂಡಿದ್ದಾನೆ ಈ ತರ. ಓಕೆನಾ? ಈ ವಾಟರ್ ಬಾತಿಗೆ what he has done, he has incorporated a pedal wheel like this. Pedal wheel ಇಟ್ಟಿದ್ದಾನೆ. Pedal wheel ಇಟ್ಬಿಟ್ಟು ಏನ್ ಮಾಡಿದ್ದಾನೆ? He kept on rotating it. ಓಕೆ, ಈ ರೊಟೇಟ್ ಮಾಡ್ತಾ ಇದೀವಿ ಅಂದ್ರೆ ಅರ್ಥ ಏನು? ಯು ಆರ್ ವರ್ಕಿಂಗ್ ಆನ್ ದ ಸಿಸ್ಟಮ್. ಓಕೆ, ನಾನು ಎಷ್ಟು ರೊಟೇಟ್ ಮಾಡಿದೀನಿ ಅಷ್ಟು ವರ್ಕ್ ಅಮೌಂಟ್ ಅವನ ಕಡೆ ನೋಟ್ ಮಾಡ್ಕೊಂಡಿದ್ದಾನೆ. ಎಷ್ಟಂತ ನೋಟ್ ಮಾಡಿದಾನೆ ಅವನು? ಎಸ್ ನೋಟೆಡ್ ಇಟ್ ಆಸ್ 10 ಕಿಲೋವ್ಯಾಟ್. ಸೊ 10 ಕಿಲೋವ್ಯಾಟ್ ಆಫ್ ವರ್ಕ್ ಅವನು ಸಿಸ್ಟಮ್ ಮೇಲೆ ಮಾಡಿದ್ದಾನೆ ಅಂತ ನೋಟ್ ಡೌನ್ ಮಾಡಿದ್ದಾನೆ. ಆಮೇಲೆ ಏನ್ ಮಾಡಿದ್ದಾನೆ, he has entirely dipped this into a water bath like this. ಒಂದು ಬೀಕರ್ ತಗೊಂಡು ಈ ಟೋಟಲ್ ಸಿಸ್ಟಮ್ ಒಂದು ವಾಟರ್ ಬಾತ್ ಅಲ್ಲಿ ಡಿಪ್ ಮಾಡಿದ್ದಾನೆ ಈ ತರ. ಡಿಪ್ ಮಾಡಿದಾಗ ಏನಾಗುತ್ತೆ, ನ್ಯಾಚುರಲಿ ಒಳಗಡೆ ಇರೋ ಒಂದು ವಾಟರ್ ಟೆಂಪರೇಚರ್ ಜಾಸ್ತಿ ಇದೆ, ಹೊರಗಡೆ ಇರುವಂತ ವಾಟರ್ ಬಾತಿಗೆ ಟೆಂಪರೇಚರ್ ಕಮ್ಮಿ ಇದೆ. ಸೊ ಏನಾಗುತ್ತೆ, ದ ಟೆಂಪರೇಚರ್ ಆರ್ ದ ಹೀಟ್ ವಿಲ್ ಫ್ಲೋ ಫ್ರಮ್ ದ ಸಿಸ್ಟಮ್ ಟು ದ ಸರೌಂಡಿಂಗ್ ವಾಟರ್ ಬಾತ್. ಓಕೆ, ಎಷ್ಟು ಹೀಟ್ ಹೋಗಿದೆ ಎಂಬುದನ್ನು ಕೂಡ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿದ್ದಾನೆ. ಅದೆಷ್ಟು, ಅದು ಕೂಡ 10 ಕಿಲೋವ್ಯಾಟ್ ಆಗಿ ಬಂತು. ಅವನಿಗೆ ಶಾಕ್ ಆಯ್ತು ದಟ್ ವಾಟ್ ಎವರ್ ವರ್ಕ್ ಯು ಆರ್ ಗಿವಿಂಗ್, the same amount of heat you will get back. So ಆಗ ಒಂದು ಲಾ ಫಾರ್ಮ್ ಮಾಡ್ತಾನೆ, the cyclic integral of work will be equal to cyclic integral of heat. This is nothing but your first law. ಅರ್ಥ ಆಯ್ತೇನೋ ನರೇಂದ್ರ?
ಅರ್ಥ ಆಯ್ತು ಸರ್, ಅರ್ಥ ಆಯ್ತು ಈಗ.
Okay. So can you write the Joules experiment on your own, everyone? It is easy, right? Okay. So that is your first law. So what is the first law, Numan Ahmed? What do you mean by first law of thermodynamics? Numan Ahmed, Sujan Rai, Sujan. I am speaking, okay. So your mic is off, I guess, okay. Malatesh. Malatesh. First law helapa.
Cyclic integral of work done is equal to cyclic integral of heat.
Very good, very good. So this cyclic integral of work flows is equals to the cyclic integral of heat flows is the first law of thermodynamics when it is applied for a cyclic process. So you understand by the word cyclic process is that cyclic process is that particular process where your initial and the final states are same. Hige hoitu 1 to 2 hoitu ಮತ್ತೆ 2 to 1 ವಾಪಸ್ ಬಂತು. So the cycle will be repeating from 1 to 2, 2 to 1, 1 to 2, 2 to 1, and such a process is known as a cyclic process. For such a process, your first law will be stated as the cyclic integral of work flows will be equal to the cyclic integral of heat flows if it is a cyclic process. If it is not a cyclic process, we shall see what it is. Okay. The same explanation is being given here. Okay, all this I can just, yes, the same thing. The cyclic integral of the work flows is equal to cyclic integral of the heat flows is being given here. And when you apply for a system, it would be dkev is equals to du plus dw. So what he says, when you apply a first law for a process, not a cyclic process. Process is a cyclic process with indifference. So if there is a PV diagram like this, okay, and there is a process going on like this. Okay, 1 to 2 hogutte, 2 to 3, 3 to 4, and 4 to 1. This is case number 1. Now, case number 2. PV diagram will be there, and here the process will be something like this. It is 1 to 2, and 2 to 3 like this. Okay, this is case 2. So in these two cases, which one is cyclic and which one is non-cyclic?
First is cyclic and second is non-cyclic.
Excellent, Pratik. So first one is the cyclic process because it is repeating in a cycle. Second one is not a cyclic process. Suppose if for the cyclic process you have just analyzed that, you can apply a first law as what? Cyclic integral of Kev will be equal to cyclic integral of W. Okay, just let me write it. What? For the cyclic process, you have learned that the cyclic integral of Kev is equals to cyclic integral of Deplev. ಅದರ ಅರ್ಥ ಏನು? How do you apply this? You can apply it likewise, man. Cyclic integral of Kev ಅಂತಂದ್ರೆ ಏನು? Kev 1 to 2 plus Kev 2 to 3 plus Kev 3 to 4 plus Kev 4 to 1. So this is nothing but your cyclic integral of Kev is equals to cyclic integral of Deblev. ಅಂತಂದ್ರೆ ಏನು? Deblev 1 to 2 plus Deblev 2 to 3 plus Deblev 3 to 4 plus Deblev 4 to 1 is nothing but your cyclic integral of Deblev. So this whole summation will be equal to this particular summation when you are applying it for a whole cycle. In this particular thing, what I am doing, I am applying it for the whole of the cycle. I am not leaving any of the process. For the whole cycle, when I apply, then the cyclic integral of Kev will be equal to cyclic integral of Deblev. Now, what I'll be doing, I want only for the process 1 to 2 2. I want only for the process 1 to 2. I am not bothered about the entire cycle. Then you cannot apply the cyclic integral of Q is equals to cyclic integral of W. Rather, you have to go with dQ is equals to du plus dW. Okay, dQ is equals to du plus dW. That means your total heat change will not be equal to total work change. There is an addition of internal energy. Okay, your total heat change will not be equal to total work change. There will be addition of internal energy. That's why dQ will be equal to du plus dW. What the meaning? Okay, how do you apply for an entire cycle? For a cyclic process, cyclic integral of K is equals to cyclic integral of W. If you just want to apply for a single process, how would you apply? dQ is equals to du plus dW. Mohan Chandra. Mohan, not there. Mervin Pinto.
Yes, sir.
Mervin. So when I want to apply it for a whole of the cycle like this, which I have highlighted, okay. So how do I apply my first law? Oh, cyclic integral of Q is equals to cyclic integral of W. That's great. So if I want to just to apply for a single process like this, which I highlighted here, I am just
dQ is
applying
equal
for.
to du plus dW.
Excellent. Nitesh Amin. Nitesh Amin. Not there. Numan Ahmad. Numan. How do you apply the first law for an entire cycle like this? How do you apply for the entire cycle like this? First law for the entire cycle.
Delta Q is equal to total work done.
Not clear. Omar Zidane. Omar. Not there. Praveen Suryakant. Praveen. Right.
Yes, sir.
Praveen.
Yes, sir.
Praveen, so how do you apply? I want to apply the first law for the entire cycle like this, which I highlighted. So how do I apply the first law?
Like dQ equal to
Cyclic of K cyclic equator. Repeat. Green.
Sir.
Left.
Sir, your voice is breaking.
Okay, I think there is work to with you. Go for a good network, Praveen. Rakesh Kumar.
Yes, sir. Yes, sir. Sir, sir, you're not audible. Sir,
Yes, now it is audible.
Yes, sir.
Yes, sir. Yes, sir.
Yara. Hoba. Nice. No, Numan. Okay. Is it not clear? Am I audible, man?
Yes, sir.
Okay. So that is how you calculate the cyclic integral of Q is equal to cyclic integral of W. First law applied to a cyclic process. And if you want to apply for just a process, it might be 1 to 2, or if I want to apply it for 2 to 3, or if you want it for 3 to 4, only for that particular process if you want to apply, then it is dQ is equals to du plus dW, where dQ is what? Change in the heat, du is change in internal energy, and dW is the change in the workflow. Since you are analyzing the work and heat, have you ever come across the value of du? That means internal energy, the concept of internal energy. Nowhere, I guess. So, the first law of thermodynamics gave birth to the value of U. That means the first law of thermodynamics gave birth to a value of U in the sense that the internal energy concept is being developed by using the first law of thermodynamics. So by analyzing the first law of thermodynamics, we have brought up a new parameter which is known as U, which is the internal energy of a system. Okay, just rub all this out. So first law of thermodynamics gives rise to which parameter? So first law of thermodynamics gave rise to the which parameter?
Internal energy.
Internal energy.
Okay, good. So that particular internal energy, whatever it is there in the system, I need to prove it to be a property of a system. What do you mean by a property? Properties are nothing but the point functions. Okay, these are nothing but the point functions. I need to prove energy to be a point function. If I'm able to prove energy to be a point function, then automatically I can prove it to be a property of a system. How to prove it? We shall just look at here. Okay, we shall see this particular thing here. In the PV diagram, there is a process given here. So it from 1 to 2 A path.
Sir, your voice is breaking.
Two different reverse path. Yes. Any problem?
Yes, sir, voice is breaking.
1. This is one particular path. Okay, so it's been highlighted. There's a problem with the internet. Not sure. Okay, is the voice clear? I mean, I think there is some nonsense going with the Wi-Fi. I guess it is being disconnected every time. I don't know why. Is everything clear now? Are you able to hear?
Yes, sir.
Let me explain it very fast. I don't know when again it goes away. So see, so 1 to A to 2, 2 to B, and B to 1 is first path. Okay, it can travel in this particular cycle. The other cycle which you can expect is 1 to A to 2, but it comes back through the path C now, 2 to C and C to 1. So these two are two different paths here. So 1A to B1 and 1A to C1. If I could prove that whatever the energy transactions that has happened in 1A to B1 is equal to the energy transactions which has happened from 1A to C1, okay, then I can prove that it is not dependent on the path whichever it traveled. Suppose if it traveled by the B also, no issue. If it has traveled by the C also, there is no issue. It only depends on the end parameters, that is 1 to 1. If I could prove that, then we can prove energy to be a property of a system. How I can prove? Nan B ಇಂದ ಬಂದರೂ ಸಹ ಅಥವಾ C ಇಂದ ಬಂದರೂ ಸಹ ಎನರ್ಜಿಗೆ ಎಫೆಕ್ಟ್ ಆಗಲ್ಲ. It will never affect the energy if I go from the path B or if I go from the path C. It will not affect the energy, the total energy of the system. If I able to prove that particular point, I can prove that it never depends on the path what you take. Rather, it depends upon the end stage, which is the point. So that's why you can prove it to be a point function and hence the property of a system. Let us see how it does. So applying the first law of thermodynamics to a cycle for 1A to B1, it is integration from 1A to 2A dkf plus integration from 1B to 2B dkf is equals to integration from 1A to 2A dw integration from 2B to 1B dw. Just I have applied the first law for what? I have applied the first law for the cycle 1A to B1. Similarly, now applying the first law for the second path, that is 1A to C1. Okay, that is same thing, man. Integration from 1 to 2, 1A to 2A, and integration from 2C to 1C, dkf, and that will be equal to the workflows. Workflows is this particular thing, and integration from 1A to 2A, and integration from 1C to 2C, dw. That is a summation of two paths, 1 and 2. Okay. So this particular process, this have taken it as 1, and this particular equation have taken it as 2. Now, if you just do 2 minus 1, so if I subtract this equation from this, what happens? You will get this particular equation here. Integration from 2C to 1C minus integration from 2B to 1B dkf, that is equals to integration from 2C to 1C dw and integration from 1B to 2B dw. So just taking dkf and dw, that means integrations of 1C to 2C on the one side. Say 1C to 2C, these two particular things has to be on the one side. On the other hand side, you have to take out, that is on the RHS, you have to take out 1B, 2B, 1B, 2B to be on the either side. So what I'll be doing, I'll be transferring this to the either side and this to the either side. Okay, so it will be as such now. Integration from 1C to 2C, integration from 1C to 2C on the same side, dq minus dw. Okay. Similarly, integration from 2B to 1B, integration from 2B to 1B, dq minus dw. Since both the integration have the same limits, I can merge these two. This is what I have done here. So integration from 2c to 1c dq minus dw, integration from 2b to 1b dq minus dw. Fine. Now, this is the interesting point here. Sir, present network issue going back. Okay, fine. According to the first law, when applied for a process, guys, when you apply for a process, what it is? It is dq is equals to df plus dw. Correct? Yes or no? Am I correct?
Yes, sir.
In this particular sentence, okay, I'll be transferring dw to the other side. It is dk minus dw is equals to du. Correct? Now,
Yes,
look
sir.
here. Look here. Here it is dq minus dw. Here it is dq minus dw. So I can replace it to be du, right? So I can write it as 2c to 1c df is equals to integration from 2b to 1b dq minus dw is what? Du again. So what I'm proving here, the energy for the path 2c to 1c and energy for the path 2b to 1b is same. That means it never matter if you come from the path B or you come from the path C, you will be having the same energy. That means you are not depending upon the path of the system. Rather, you are depending upon the points, that is 1 and 2 at the end state of the system. So that's why energy is a point function, hence the property of a system. Got it? Got it, everyone?
Yes, sir.
Yes, sir.
So overall fund of all the explanation, what you have to prove is, if you go by the path B or you go by the path C, the end result, the energy, the change in the energy will remain same. Irrespective of the path you have taken, if the energy is remaining same, then path has no significance on the energy, right? It has no significance on the energy. That means it is not a path function. It should be a point function. So that is the point how you develop all this theory, man. Clear? Simple, man. Just apply for this particular cycle once and apply for this particular cycle once. Do 2 minus 1. Subtract those two equations. You will get this particular equation where you can prove the du is equals to du. That means energy from the path C is equals to energy from the path B. Then you can prove it is not dependent on the path. It is dependent on the point. That's why it is a point function. Understood? Any doubts in this particular explanation of energy to be a property of a system? Any doubts?
No, sir.
Okay, good. So make sure this particular question is very important. It has been asked many, many times. So hopefully in the internals. Okay. 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 So internal energy, what is internal energy? If in case if he asks in the examination, what do you mean by internal energy in the sense? So you have to be in a position to just write. It is the heat energy that is stored within a system, within a gas or a system. What is internal energy? It is the energy which is stored within the system for a particular period of time. So that is your internal energy. Okay. Battery is draining out. Okay. And what do you mean by enthalpy? Enthalpy is the total heat content of the system. You already learned this definition, I guess, in the module 1. I have taught you, right? I have discussed about the enthalpy, right, in the first module? Yes or no, man? So H you indicate it by enthalpy. Enthalpy will give you the total heat content of the system, which is given by internal energy plus P into V. That is, P into V is nothing but your work done. So H is equals to U plus P. We always do remember this expression. It is very important. Muhammad Khalid, how do you calculate enthalpy?
Sir,
How do you calculate enthalpy, dear?
is equal to U plus P, sir.
H is equals to U plus PV. That is very good. Sohan,
Yes, sir.
so how do you calculate enthalpy?
H is equal to U plus P.
Yes, this particular value is there, right? Which is the value of U. U is nothing but your internal energy. And remember, there is a strange thing about the internal energy. What is that strange thing is, suppose if there is a system, okay, just take the pen. If there is a system and it has a specific value of internal energy as 20 joules, you see, it has an internal energy of 20 joules. If I change the pressure, the internal energy will not change. If I change the volume, the internal energy will not change. If I change the mass, the internal energy will not change. If I change the density, the internal energy will not change. If I change the chemical composition, the internal energy will not change. But if I change the temperature, that means if I heat or if I lose the heat from the system, your internal energy will change. This is a very beautiful point about the internal energy. Okay, so internal energy, when does it change? Only when the temperature of the system changes. If and only if your temperature of the system changes, then only your internal energy will change. So this particular point is very important. That's why they say internal energy is a function of temperature alone. Okay, Sushant Shetty. Sushant.
Yes, sir. Tell me.
Sushant, so if I want to change the internal energy of the system, which parameter I should change, man?
Yes, sir. Tell me. Tell me, sir. Yes, sir. Temperature.
Temperature. Very good. Very good. Okay. Now, so there is a small bit of derivation. You can just look into it. This also is important, where you'll prove that dq is equals to dh. Okay. Now, we shall look into the different applications of the first law on the different processes. Okay. So when you apply the first law on different processes, say now here it is isobaric, which is number one. Second one is isochoric. Okay. Third one is isothermal. Okay. Fourth one is adiabatic. And fifth one is the polytrophic. So how do you apply the first law of thermodynamics for all these five processes? So application of the first law to all these five processes will lead you to calculate what is Kiv 1 to 2 for isobaric. Okay, what is Kiv 1 to 2 for isochoric? What is Kiv 1 to 2 for isothermal? What is Kiv 1 to 2 for adiabatic? What is Kiv 1 to 2 for polytrophic? So applying the first law of thermodynamics, you will be in a position to derive the expressions for all these five. What is Kiv 1 to 2, that is heat lost or gained from 1 to 2 for all the five processes. Let us look this in a very brief. There is very limited possibility that they might ask it, but yet I have given it in the form of the notes. So we will go very fast at this, and remember only the end results if possible. Okay, so here it is. So when you apply, what is the work done from 1 to 2, which is isobaric, man? Come on, let's see. Work done from 1 to 2, which is isobaric. Just a minute, I'll just come back. Okay, guys. No. I was in the call. Okay, there's a call. Am I audible now?
Yes, sir.
Okay. So let us see, man, in the brief. What is the work done from 1 to 2, which is isobaric?
W is equal to P of V2 minus V1.
W is equals to P into V2 minus V1, which is same thing substituted here. So applying the first law of thermodynamics, battery is running lower. Okay. So W is equals to dQ is equals to du plus dW. Is it this? This is the first law. When you apply it for a process, not a cyclic process, just a process. If you apply it as what? dQ is equals to du plus dW. So in this particular expression, the same thing is being applied from 1 to 2, which is isobaric here. So it is Q 1 to 2, that is equals to W1 to 2 plus change in internal energy. Now, so W1 to 2 is what? P into V2 minus V1, which I've just said. So this is U2 minus V1. So multiplying it, it will be P into V2, and it is P into V1 here. U2 minus U1 as it is. So taking, you can just write it as U2 plus P2 V2, that minus U1 plus P1 V1. Correct? You can write it as such. Now, what is U plus PV, man? Recently, in a short span, we have discussed what is U plus PV. What is U plus PV?
Enthalpy.
Huh? It's enthalpy.
Enthalpy.
So the whole thing, U2 minus P2 V2 can be written as H2. Similarly, U1 plus P1 V1 can be written as H1. That means Q1 to 2 I can calculate to be the difference between the enthalpies between states 1 and state 2. So if I want to calculate the heat transfer from the process 1 to 2, which is isobaric, what should I do? I can calculate by subtracting the enthalpy at state 2 and state 1. That means the heat transfer for an isobaric process is given by the change in the enthalpy. And for the isochoric process, if you observe, it is given by change in the internal energy. Remember, guys, for isobaric, the heat flow is given as the change in enthalpy, whereas for the isochoric process, the heat flow is given as the change in internal energy. Why change in internal energy? I can prove this. When you apply, what is the first law applied for a process? dQ is equals to du plus dW. Okay. Now, applying it for a, which one? Isochoric process now. Change in internal energy is U2 minus U1 plus dW1 tandre W1 to 2. Now, what is W1 to 2 for isochoric process? What is W1 to 2 for an isochoric process? Yes, guys. What is W1 to 2 for an isochoric process? What is W1 to 2 for an isochoric process? Zero, right? Zero. So Q1 to 2 for an isochoric process is just U2 minus U1 because this is 0 here. So that's why, how do you calculate the heat transfer for an isochoric process? You need to subtract internal energy. How do you calculate the heat transfer for an isobaric process? You need to subtract what there? You need to subtract. What do you need to subtract there?
Energy.
In isobaric, you need to subtract the enthalpy value, whereas isochoric, you need to subtract the internal energy value. That means the heat flow in an isobaric process is given by the change in the enthalpy, whereas the heat flow in an isochoric process is given by the change in the internal energy. Clear with these two concepts, everyone?
Yes, sir.
If there are any doubts, let me know. Next, let us move to the isothermal process now. For an isothermal process, if I apply dq is equals to du plus dw. Okay. Previously, I have just consulted and explained you about the relation between the internal energy and the value of temperature. What was that relation? What is so mysterious about the internal energy and the temperature between these two parameters? What is that thing? Sujan. Sujan, Ashir, Hazim. So what is the strange thing about internal energy and the temperature, the relation between these two parameters?
Directly proportional. Internal energy is directly proportional to temperature.
Okay. Rather, I can say that your internal energy will never change if I change the pressure. It will never change if I change the volume. That means it is independent of all the parameters except the value of the temperature. That means if you change the value of temperature, only and only and only then your internal energy value would change. So if you wanted to change the internal energy, what do you want to change?
Temperature.
Temperature. Are you changing the temperature in the isothermal process?
No, sir. Constant.
No.
There is no change in the temperature. So if there is no change in the temperature, will the U value, that is internal energy value, will change?
No.
No.
As simple as that. So that's why what happens, your dq value will be equal to dw value in case of isothermal process. That means all the 6 expressions were there, right? All the 6 expressions. Remember those 6 expressions to calculate the isothermal process workflow. Remember or not?
Yes, sir.
Same those 6 expressions can be used to calculate even the value of Kiv also, even the value of heat flows also. That means the expression for calculating the value of W is equals to the expressions of calculating the value of Kev in case of what? In case of isothermal process. Clear, guys?
Yes, sir.
Understood? Okay, there are last 2 process, guys. Please have a patience. Will you give me another just 5 minutes so that I will be completing the last 2 remaining? There are no derivations, just the concepts. Only 2. And we will summarize all the things within 5 minutes. Okay? Is that okay? 5 minutes. 5 minutes.
Yes.
Okay. Don't lose the patience, guys, because this is so important, so important. So understanding the heat flows of all the 5 processes. Until now, we shall just have a recap. Number 1, isobaric process. How to calculate heat flow? Sir, I will calculate with change in enthalpy. Very good. Second, there is an isochoric process. How do you calculate the heat flow? Sir, I will calculate with change in internal energy. Very good. So third, isothermal process. How do I calculate my heat flow? Sir, the work done expressions is same for the heat flow expressions. So I would be using any one of all the 6 expressions to calculate my heat flow. Very good. Let us now go into the next process. Which is the next process, guys? Which is the next process?
Adiabatic.
Adiabatic. See, name the process where the workflow is 0. Name the process where the workflow is 0.
Isochoric.
Huh?
Isobaric.
Hey, Sujan.
Isochoric.
Isochoric. Name the process where the workflow is 0. Your answer is isochoric. Now listen this carefully. Name the process where the heat flow is 0. Then your answer should be the adiabatic process. Okay? Got it? Adiabatic process is a process where your curve 1 to 2, which is adiabatic, if you want to calculate, you can just straight away put 0 for that. Why? Because heat flow for an adiabatic process is 0. Name the process where the workflow is 0.
Isochoric.
Name the process where the heat flow is 0.
Adiabatic.
Very good, very good. Okay, now coming to the polytropic work done. So polytropic work done, you have a short derivation. If you can just look into it, not a big issue. So how do you calculate the polytropic work done? It's very simple. So this is the value of gamma, right? This is the value of gamma, which is known as the ratio of specific heats, which is Cp by Cv, right? That is equal to gamma. Now, Kev, I'll just take the teaching board. So Kev 1 to 2 for a polytropic process, I must calculate now. Okay, how do I calculate? I have to multiply W1 to 2 of a polytropic process into gamma minus n divided by gamma minus 1, where n is the polytropic index, 2, 3, whatever will be giving in the question. So that is the value of n. So how will you calculate the polytropic heat flow? Yes, you have to multiply. First, you have to calculate what is polytropic workflow. Then you have to multiply it with gamma minus n divided by gamma minus 1. Clear? Clear, guys? So what is polytropic work done from 1 to 2? I can write it as P1 V1 minus P2 V2 divided by gamma minus 1. Yes or no? Sorry, n minus 1. So this is the polytropic work done into gamma minus n. If you multiply divided by gamma minus 1, so we'll get what is known as the heat flow for a polytropic process. Let us have a very quick recap for all the different processes heat flow now. Okay, now isobaric process. How do I calculate the heat flow? Come on, guys. How do you calculate the heat flow for an isobaric process? How do I calculate the heat flow for an isobaric process? It is given by change in
enthalpy.
Very good. It is given by the change in enthalpy.
Change in enthalpy.
Very good. So now, how do I calculate the heat flow for an isochoric process? It is given by change in
Internal energy.
Very good. It is given by change in internal energy. Now, how do I calculate the heat flow for an isothermal process? How do I calculate? Anish, yes, ma'am.
So using any one of the work formula.
Yes, you can use the work done formulas itself because your curve will be equal to W in case of isothermal process. So you can use the same work done expressions to calculate your heat flow. Very, very good. Now, how do I calculate my heat flow in an adiabatic process?
0.
Very good. So the process in which the heat flow is 0 is the adiabatic process. Now, how do I calculate the heat flow in case of a polytropic process? Polytropic.
Gamma minus n divided by gamma minus 1.
Exactly. So you have to multiply gamma minus n divided by gamma minus 1 To what? To the polytropic work, that is P1 V1 minus P2 V2 divided by n minus 1. So for that you have to multiply gamma minus n divided by gamma minus 1 in order to calculate Q1 to 2 for a polytropic process. Everyone take the screenshot of this particular thing. It's so and so and so important. Keep it with you. Okay, we should discuss the remaining things in the next class. Okay, till then, take care. Don't worry about the attendance. Attendance will be taken in the next class. Okay, in the next class, we'll be deriving the most important expression, which is known as SFEE, steady flow energy equation. Till then, enjoy your time. Have a good day. Okay, take care, guys.
Thank you.
Thank you, sir.
Sir, attendance.
Attendance will be taken in the next class. Don't worry, man. Don't worry about the attendance. It will be taken.
Sir, Prakyat present.
Right, Prakyat.
Sir, Akash present.
I will mark you, man. Don't worry about that. I take the screenshot of this. This is very important.
Present, sir.
Hey, ತಗೊಂಡೇ ಇಲ್ಲ ನನ್ನ attendance. ನಾನು ಇದು extract ಮಾಡ್ಕೊಂತೀನಿ, auto extract ಮಾಡ್ಕೊಂತೀನಿ. There's a feature in the Google Meet where you can extract attendance. Okay? Don't worry.
Thank you, sir.
Yeah.